I've already started. All right, so when we are determining the general equation or the general solution to the differential equation, we are trying to get it in the form of having the y's on this side with dy and the x's on this side with dx. That way we can get to this point where we can integrate them. If you hear any strange noises, that's just Mick Diamond living his best life. So I'm going to take this one up and move him across there, and I'm going to take this one up and move him across there. Okay, and that will give me these equations down here. Stop with the whistle! The kids are going to hate you when this is in their ears. Like I said, I'm only recording this once. Okay, now we have it in this point, we can integrate both sides, and because we're integrating, that means we want to add on a constant. Now, I only have to add one constant on because the general solution is to get it in the form of c equals. So once I've got it to here, I can shift this term and this term across to the other side, making them negative, and I'll be left with c is equal to. Now, if I'd done this on the other side, it would be the same. It just means that I would have c is equal to, and this would be negative, this would be negative, and this would be positive, and this would be positive. And that's fine because when we work out c, it'll just invert whatever that answer was. Now, for example 18, we're going to do the same thing again, get our terms on the other side. So first one that I'm going to move across is I'm moving the y across. Then I'm going to factorize y out so I can separate the x's and the y's. Otherwise, we'd have to use chain rule, and that's more complex than what we want to do. So I move these terms over to their respective sides, and that leaves me with my integrals. So now I can integrate my functions. This side will give me ln y, this side will give me 2x cubed minus x plus c, and this time I'm not trying to work out the general solution. This time I am substituting in when x is 0, y is 1. Substituting that in will let me work out what our constant value is. So down here, I chuck those values in. That gives me ln 1 is equal to 0 plus c. So then c is equal to 0 because ln 1, if I think about what's actually happening, that's a log function with base e, 1. And if I rearrange this, I get e to the power of x is equal to 1, meaning that x has to be 0. So they've jumped a little step there. Now that I've got that answer, I can rearrange this in terms of y, and that's generally our favourable choice. So if you can get it in the terms of y is equal to at the end, we like to do that. Now, worked example 19, I've got two possible solutions for you. So my solution is different to what they've done in the textbook. In this case, we're first going to rearrange so that we can integrate both sides. So again, I'm separating my x's and my y's from each term, which will give me this down below. Now, the next step is where it gets slightly different to the textbook. Here, I've chosen to have that as negative 2x, and over here, this is a positive 1. Now, if you look at the formula sheet, you'll be able to see that this form is integrated into an arcsine function. So that's how I've chosen that. This is equal to negative x squared plus c. And that gets me this function down below. Now I'm going to use that fact that they gave us, that when x is 0, y is 4, because I've got my general form, and I'm going to put that back in to determine what my constant is. Now, because I've chosen the sine function, I'm going to work out that c is equal to pi on 2, because sine of negative 1 is equal to 90 degrees or pi on 2. Okay, so the last part of this question is to find the largest domain for where the solution is valid, and we want to look at those possible values. Now, one of the first things that we have to recall is that our arcsine functions have a set domain of possible answers. So for an arcsine function, that domain falls between negative pi on 2 to pi on 2. So once I've got that, all I'm doing is rearranging my equation. So now I'm taking the sine across, and I'm going to take the 4 across, and that gives me this form down here. Okay, so to find the x values between our arcsine domain, I'm now going to put the possible domain for the arcsine function on this side, and I'm going to solve for the bracket inside. So this is the bracket inside that I'm talking about. These arcsine values are just over here. So first one that I'm going to move across is this pi on 2. It comes across by subtracting, meaning that I'm left with negative pi and 0. Then I'm going to take the negative across, which will leave me with pi and 0. Then the next one, I'm going to take the square root of both of these functions. Square root of 0 doesn't do anything, which is why I'm left with x is equal to root pi 0. So that's our domain. Now, the step that I want you to be cautious of is this one at the very start. So if you have something different to the textbook, it doesn't mean that you're wrong. It just means that someone was probably distracting you while you were trying to do this. So we've come too far. I'm not recording a new video because of this. Okay, so this is the step where we could have done something different. So if you've got your little piece of paper next to you, I'd like you to note this part down, because the thing that is different between this and their example is in this step here, they chose to move it across differently to make this side positive 2x and then this side negative 1 over this. Now, if you look back at your specialist formula book, you'll see that this integrates to a cosine function. Now, we're going to be applying the same steps, except when you're using it as the cosine function and you substitute these values in, you end up with your constant as being 0, meaning that your function will work out like this. And when I start to look at the range that's possible for this, the arc cosine function has a domain of 0 to pi. So I'm using the 0 to pi instead of using negative pi on 2 and positive pi on 2. But it will still get you the same answer just like you got down here.